Ready, Konstantin?
Yeah.
Okay, so welcome everybody to the last session of the day. So our first speaker is Konstantin Bogdanov, and he's going to tell us from the university, well, Aix-Marseille Université, and he's going to tell us about transcendental dynamics and iterations on infinite dimensional Teichmüller spaces. Whenever you want.
Hello, everybody. First, thanks to the organizers for this nice event, organized it during the pandemics. Hopefully next year it will be possible to go to Barcelona physically. So I am going to tell you about my recently finished project on infinite dimensional Thurston theory, which might be sort of a tool that makes use of the Teichmüller theory, infinite dimensional Teichmüller theory, to prove certain classification results about singular escaping dynamics of transcendental entire functions. So the talk is structured in the following way. First, I give you a little bit of motivation from the point of view of holomorphic dynamics of what I'm going to prove, what kind of classification results. Then I tell you exactly about the main theorem, which I call classification theorem. Then I try to motivate this classification theorem from the other point of view, from the point of view of Thurston theory. And afterwards, I tell you a little bit about the proofs, about the ground scheme, how it works, and maybe about one of the most important ingredients of the construction, the invariant compact subset. So let us start. So, well, as you know, in holomorphic dynamics, we very often not only want to study every holomorphic function separately, but rather want to study parameter spaces of functions. Well, maybe the most important example of such a parameter space is, of course, the Mandelbrot set, which is a space of complex parameters C, for which the iterates of the critical value of the polynomial z squared plus C is bounded. Yeah, so well, here it's in black, and yeah, many people study Mandelbrot set, and in particular, people are interested in the boundary of the Mandelbrot set. But one way to understand better the boundary of the Mandelbrot set is, of course, to study the complement of the Mandelbrot set and to study its boundary, which is the same. So, and what's known about the complement of the Mandelbrot set? So, well, this quite standard result is that every quadratic polynomial corresponding to parameters in the complement of the Mandelbrot set can be characterized by its speed of escape or potential and its combinatorics or external angle. And these parameters that have the same combinatorics are united in a curve which is called external ray. Here you can see some of them. So, and now you can ask just a blunt question, maybe, is there a similar characterization via speed of escape and combinatorics possible for parameter spaces of transcendental entire functions? So, well, it turns out that the answer is yes. And for certain families, at least for certain families of transcendental entire functions, and this is the main result of our project. Well, before switching directly to this classification theorem, let me just remind you what are the interesting explicit families of transcendental entire functions that people usually study. So, well, the simplest one is, of course, the exponential family, e to the z plus kappa. This is the analog of the polynomial z squared plus c in the polynomial case. Also, people study cosine family, structurally finite maps. But for us, of interest for us in this talk would be the family of functions which are compositions of polynomials and exponential. Well, in particular, exponential family is in this family for polynomial degree 1. So note that every such function is of finite type. That is, its singular value, set of its singular values is finite, and more precisely, it has exactly one asymptotic value and, well, a few critical values, possibly 0, as for the exponential family. On this picture, you can see the example of a part of a parameter space for the exponential family. Here you can see some of the parameter arrays. These are curves that that correspond to the parameter which escape parameters which escape with the same combinatorics, but with different speed of escape. So as you and here you see this sort of transcendental analog of the complement of the Mandelbrot set is has much more difficult topological structure. It's basically these curves are joined in the contour bouquet that well, you've seen them in the previous talk. So this is something, this is a topologically more difficult object than the complement of the Mandelbrot set. Yeah, but well, in my project, I do not really study the topology of these parameter spaces, but rather the realization, what kind of functions are realized. So here is the main theorem. I call it classification theorem. Let me read it together with you and then give a few comments. So given some polynomial p and entire function, which is the composition of p with the exponential, and assume it has m finite singular values, well, immediately this function defines its own parameter space. And given also a list of m allowable speeds of escape and combinatorics via m potentials and external addresses, each corresponding to a particular singular value f naught. So when if we have this type of information, then the claim is that in the parameter space, there is a unique entire function g, such that each singular value escapes exactly with the prescribed combinatorics and speed of escape. So, and conversely, that every function in the parameter space such that its singular values escape fast. I implicitly mean on disjoint trace, but I don't want to give you a definition of disjoint trace for now. Yeah. So this function is one of these. One more comment on this vague word allowable. This is not really so this is not really the way to somehow restrict the generality here. This is just the way to choose the proper external addresses so that if the functions are realized, the escape is on disjoint trace. So it's not something that restricts the generality of the result. Yeah. So and to prove this theorem, one could study a special map called Thurston sigma map, acting on infinite dimensional Teichmüller spaces. So this is inspired by the classical Thurston's characterizations of rational functions. And now I talk a little bit about this classical theorem. So, Thurston theorem. So, post-critically finite branched covering of the two-sphere is Thurston equivalent to a rational function if and only if there is no Thurston abstraction. So, well, here is a reminder that what is Thurston equivalence. So, critically finite branch covering F is Thurston equivalent to a rational map G is this homomorphisms Psi and Psi such that G is of this form and Phi is isotopic to Psi relative to the post-critical set PF. So, so far so good. But now we can, for example, just independently think about this result because it's interesting in its own right and ask like simple-minded question. What if the set PF is infinite? So can we prove somewhat analogous results? Yes, the answer is yes, and but the change from this finite to the infinite setting, it leads to quite a big theory because, well, simply because there are many more different covering models that might be realized. Because if we have post-critical set infinite, we in addition have an infinite covering degree possible, and so there is a big field to explore. But remember that we wanted to prove the classification theorem. So in fact, we are only interested in branch coverings that somehow model the transcendental entire functions that we want to be realized, that we want to find, that are realizing the escaping dynamics of the singular values. So we do not prove the theorem, some analogous theorem to the classical Thurston theorem for just arbitrary topological branch covering, but instead we use this data from the classification theorem, that the speed of escape and combinatorics, and some map from the parameter space to construct a quasi-regular branch covering F. And then this map F defines a special sigma map acting on the Teichmüller space of the complex plane with the set PF removed. Well, in this case, PF is an infinite set of punctures. So, and here, unlike in many other cases, here this goes analogously to the classical theorem that, and to the proof of the classical Thurston theorem that if we find the fixed point of the sigma map, then it will correspond to the transcendental entire function with singular escape in dynamics modeled by quasi-regular branch covering F. That is exactly the transcendental entire function that we are looking for. So roughly speaking, the classification theorem is reduced to this theorem. Yeah. So before, let me remind you a little bit about what is the Teichmüller space that we consider. So we consider the Riemann surface C minus PF. In our case, PF is an accountably infinite set convergent to infinity. So basically, C minus PF, it's a complex plane with infinitely many punctures, and these punctures accumulate only at infinity. And the Teichmüller space TF of this Riemann surface is a set of quasi-conformal self-homeomorphism of C, modular composition with an affine map and the isotopy relative to PF. So this is quite standard definition of the Chmüller space. Next, what you should remember about this Teichmüller space for this talk is that it is there is a special Teichmüller metric on the Teichmüller space, and out with this Teichmüller metric, TF is a complete metric space. Yeah, here is the reminder for you how exactly this Teichmüller distance is defined. So. And now on this table, I wanted to just briefly show you what are the main challenges that appear when we switch between finite and infinite dimensional Teichmüller and Thurston theories. Well, the first one, maybe the most obvious one, is that in the finite dimensional case, the mapping class group is finitely generated, while it's infinitely generated if PF is infinite. So it already should ring the bell that it might be not easy to describe the homotopy information given by the point in the Teichmüller space. Another remarkable thing about this is that in the finite dimensional case, there is only one Teichmüller space, because every homeomorphism in its isotopy class contains a quasi-conformal map. But this is no longer true for the case of infinitely many punctures. And this leads, due to this, there are infinitely many different Teichmüller spaces. So another things that are important to study the geometry of the Teichmüller spaces is are Teichmüller existence and uniqueness theorems that are well known since long ago, but there are not really there is no general theory in the infinite dimensional case. We know something about special cases via Strebel's frame mapping theorem, which is sort of some special variant of Teichmüller existence theorem. And further, regarding the Thurston theory, is that even to set up the sigma iteration, it is no longer enough to have only topological information about the branched covering. One needs a topological information and the QC type of information. And the last thing is that the main ingredient in the proof of the classical Thurston's theorem is the statement that sigma or sigma squared is globally strictly contracting, which basically follows from Teichmüller's theorems. But in the general case, I don't know whether this is true. So now I tell you a few words about the about the general scheme, how to prove the classification theorem. So, so first we define a quasi-regular branched covering F that models the desired mode of escape of singular values, and using it set up the Thurston iteration via sigma. Then we construct a compact subset CF in the Teichmüller space that is invariant under sigma. Then we prove that the restriction of sigma on CF is strictly contracting in the Teichmüller metric. And finally, we prove that there is a unique fixed point of sigma on this CF. And afterwards, we show that this fixed point corresponds to the entire function that we are looking for. Well, existence of the unique fixed point follows just simply easily from 2 and 3, because well, in 2 is then, because then sigma is strictly contracting continuous function on a compact set. So the uniqueness of the existence of the fixed point follows simply by Banach fixed point theorem. So now let me, out of this 4 ingredients, the most difficult, the most technically difficult and the most demanding is item 2, because the construction of the compact invariant subset. Let me tell you a little bit about the first 2 ingredients, about how does it work, in general. So set up the Thurston iteration. So we have some transcendental map F naught of the form P of X, where P is a polynomial, and V1 to Vm are its singular values. Well, we might assume that they do not escape because we are interested only in the parameter space. There's always a function in the parameter space for which singular values are not escaped. So in the exponential family, for example, you can choose this function. So, well, here I have exponential because it's our sort of toy example for which everything is easier. We will return to it a few more times. So, and then how goes the setup of the iteration? So in the escaping set of F naught, we choose points Q1 to M points that escape with exactly the prescribed speed of escape at combinatorics that we had as input data in the classification theorem. Then we define a quasi-conformal map, which we call capture, such that it maps each singular value Vi to Qi, and also it does not spoil combinatorics in some sense. Then we consider quasi-regular map, which is a composition of this capture with F naught. Then its singular orbits will coincide with orbits of points Q1, Qi under F naught. So this is the way how we construct our quasi-regular map. So for the exponential family, yeah, maybe I should introduce some notation. For the exponential family, we denote the post-singular set of this quasi-regular map PF by AN. So, and then the Thurston iteration is can be set up exactly as in the classical Thurston's theorem via the Thurston diagram. So, in fact, we take a quasi-conformal representative phi in the Teichmüller space. Then the composition of phi with F defines a complex structure here upstairs. And then from the uniformization theorem, there is a straightening map phi tilde. In fact, it turns out then the map G, which is basically the composition of these 3 maps, it will be entire map, a holomorphic entire map. So, and then this correspondence of phi to phi tilde is induces a well-defined map on the level of the Teichmüller space. For the exponential family, we really have an explicit formula for this. And we can recover phi tilde from phi. Well, of course, under special normalizations. Well, note that the analogous setup is not possible for arbitrarily topological transcendental entire functions, because in this case, one still gets some well-defined map sigma, which acts on the isotopy classes of homomorphisms, but it might be the map between different Teichmüller spaces. This is the predicament here. So, okay, so let me run out of time, so let me skip maybe one slide. So, let me maybe tell you just a few words about the construction of this compact invariant set for the exponential family. So the simplest one, the toy example. So in fact, here, as you might remember, A0, A1, and AN is just a singular orbit that we want it to, and we want it to be realized via a transcendental entire function. And then what we do is that we find one big disk D rho, which contains inside of it just finitely many punctures, and we also we surround the punctures outside of this big disk, every puncture by small disjoint disks around them, so that in the big disk we have some finitely many punctures, and here in every small disk we have only one puncture. This is possible because the escaping points of the exponential map, they escape fast. So this is what we have, and then how do we consider the quasi-conformal maps that we obtain from identity map in the following way. So we allow the points outside of D rho to move only in the corresponding small disks here and here, while for the map inside of D rho, we allow them to move inside of D rho, but with another condition, that the points cannot come too close to each other, and they cannot wind around each other too much in a way. So in a way, this is sort of a decomposition of this compact invariant set. This is a set CF into the two subsets of different Teichmüller spaces. The one Teichmüller space is just a Teichmüller space of the disk D rho with finitely many punctures. And this subset is contains only those homomorphisms that that fix the boundary of D rho. And we consider some bounded set in this Teichmüller space. So this exactly forbids the points to come too close to each other and to rotate around each other. Well, and another Teichmüller space of the complement of D rho and the punctures. And in fact, there we again forbid to the homomorphism to so we assign the homomorphism that fix the boundary of D rho. And here, this since basically the position in the Teichmüller space is defined by the positions of these points, that since they are moved in the disjoint disks. So it will be basically a small piece of the moduli space. So it's like we have a decomposition to two types, just one more chaotic part where the points are allowed to wrap around to each other and to do somewhat more things, and the one where we have infinitely many points, but these points are almost fixed. So let me come to the conclusion then. So well, in our project, we classify all entire transcendental functions of the, which are compositions of polynomial and exponential, for which all singular values escape fast, and this is given in the classification theorem. Then, well, the key to the proof of this theorem is to somehow to prove an analog of the Thurston's characterization theorem, but for the singularly infinite case, well, and also the case of infinite degree, covering degree. Well, and this involves iterations on infinite dimensional Teichmüller space. So, well, due to this infinite dimensionality, there are a lot of different challenges to solve. If one wants to really reprove the classical theorem, so there is another way is to deal with it is basically not to deal with them at all, but rather to find a way around by constructing a special subset in the Teichmüller space, so that in this subspace, these challenges are easier to deal with, and that they're somehow more tame. So, yeah. So, and yeah, and we also expect that these techniques can be applied to more general families of functions, and this quite explicit family of compositions of polynomials of exponentials. Maybe the first candidate, of course, would be, well, the good candidate would be functions of finite type and finite order, because in that case we have an escape of on race, and this is one important ingredient of the proof. So based on this project, there are 4 papers. 2 of them are already on the archive, and 2 more will be uploaded quite soon. So yeah, thank you.